I think we're at the start of this session, and our first speaker today is Marjan Asgari from the University of Guelph, who will be presenting on distributed watershed hydrologic models. So Marjan, you can take it from here.
Hi, everyone. It's my pleasure to present our recently published study, which is development of a knowledge-sharing parallel computing approach for calibrating distributed watershed hydrologic models. Watershed hydrologic models have been increasingly developed to study landscape processes such as runoff, sediment, and nutrient processes. Even though these models provide precise results for predicting water quality and quantity in watersheds, their calibration process is computationally expensive. There are some reasons for this computational demand, such as the excessive spatiotemporal heterogeneity of predominant hydrological processes in these models, using global meta-heuristic optimization algorithms for calibrating these models, using high-resolution data sets, and working on large watersheds. Parallel computing has been increasingly applied to address these computational challenges of calibrating watershed hydrologic models. However, if we dive into the literature, we'll see the lack of knowledge sharing among parallel computing units. In fact, as the meta-heuristic optimization algorithms are population-based, they have a corporation phase in which individuals should transfer knowledge they have gained in exploration of the parameter space in order to guide the whole population to the optimum region in a parameter space. But we see in the literature that the corporation phase in which the information should be transferred among parallel computing nodes, considering each parallel computing unit is working on a single individual, is missing. And the reason for that is the use of MPI in parallelization studies in calibration of watershed hydrologic models. The fact is that the knowledge transfer should be one-sided because the nature of the parallel calibration of hydrologic models is asynchronous. But MPI parallelization approach is two or double-sided, needs double-sided communication, which doesn't provide efficient performance for parallel calibration. And we see that researchers have deleted that part, or the corporation phase. We also see the lack of high programmability of youth frameworks because hydrologists are not programmers, and they want to work with programming languages which have high programmability, but we don't see that because most of them are working with MPI and like C or C++ for parallelization, and the lack of high parallel efficiency and the capability of handling failed nodes. Partition global address space paradigm had not been implemented in this field. So we use Chapel programming language, which implements this paradigm to address the current research gap. For calibrating, this is our conceptual framework. For calibrating a hydrologic model, optimization algorithms need to iteratively modify the values of the calibration parameters, run the model simulation, calculate the objective functions, and guide the search to the most optimum region in the parameter space. So it's iteratively, we have to run model simulations iteratively. But as we see here, the algorithm needs to have the current parameter set and needs to modify the current parameter set with some knowledge of all the best parameter set or all the optimum parameter set that have been found so far. So we have the current parameter set, we have the best parameter set, which is based on the knowledge, and then we modify that, run the model, and this process continues. But if this best parameter, or if this knowledge is only the knowledge of one locale, it's not the best. So we need that. We need the knowledge of all the locales to be shared with all the locales when they are modifying the parameter set. So we need all the locales send their information to locale 0, and then a locale 0 updates its database and finds the most optimal parameter set and shares among all the other locales. And also, because all the locales are searching the same parameter space, we should avoid redundant exploration. So locales need to also communicate with each other about the neighborhoods that they have explored. So we use CHIUW allows us to take the advantage of the shared memory access instead of sending receiving message for the fast knowledge sharing. So for the knowledge sharing between locale 0, so our conceptual framework is consisted of locale 0, which is only the manager, and all other locales. So for the knowledge sharing between locale 0 and all the other locales, which is the best or the knowledge of all the exploration, we developed a listener thread, which we actually developed an asynchronous and real-time access by developing a listener thread by multi-threading feature of CHIUW. This thread on each locale constantly is listening to locale 0, and as soon as the availability of the knowledge on locale 0, the locale reads that information and updates its variables. For the knowledge sharing between locales, there is a memory sublocation on the locale 0 for each locale. Then each locale, whenever each locale wants to share its knowledge, it sets a lock to prevent other locales from reading its container. Then it checks the size of the container. If it's reached limit, it empties that container, and then it writes its knowledge into that container and unlocks the container. And whenever the locale wants to read the other locale's knowledge, it checks their lock, reads the knowledge, and unlocks the container. So we developed these two threads for our program. But something that we faced in our research was the challenge of CHIUW queue threads at tasking layer for running hydrologic models. During our research, we faced huge running times for running our external hydrologic models in our CHIUW sub-processes. So we learned that queue thread tasking layer in CHIUW pings CHIUW threads to all the CPUs available on each locale to provide optimum affinity and high performance. However, for the studies that the extensive or the CPU intensive part of the program is carried out in CHIUW sub-processes like our study, this pinning behavior should be modified. So we learned that we need to set these two environmental variables in order to decrease the running time of our external model. So I just need to. In our research, setting these two variables led to high performance improvement in our running model. The runtime of our hydrologic model simulation for an 8-year calibration period decreased from 65 minutes to 13 minutes on a locale with 12 CPU cores. So some of our results, I'm going to present some of our results. The first is a communication overhead, because for knowledge sharing, the communication overhead should be low, which CHIUW provides low communication overhead, as you see here. But based on a study, we learned that the communication overhead in CHIUW can be impacted by the network latency. So in our study, we used Compute Canada, Cedar, and Graham clusters. The Cedar cluster provides the omni-path network with latencies of few microseconds, as you see the red ones here. And the Graham cluster provides an InfiniBand network with latencies of less than 1 microsecond. Still, both clusters are providing low communication overhead, but we see that Graham cluster provides better communication overhead, which proves the previous conducted studies.
Hey, Marjan, sorry to interrupt, but we just have about 30 seconds left here for questions.
Okay,
so if you could wrap
that's all. Yeah. And the other result that I wanted to share is that our speed up gain and the parallel efficiency that we have. As you see, we achieved linear speed up for parallel systems with 3 and 4 locales, super linear speed up with systems with more than 4 locales. And also we achieved more than 75% parallel efficiency for our program. Thank you for listening.
All right, thanks, Marjan. That was a great talk.